Okay, welcome to Oceanography. We're carrying on with our lectures. We have two topics to cover. I'm going to briefly catch up on the material that I presented last week, last Tuesday, talking about light levels and light attenuation. And the example that we gave, what the topic we were discussing was the way in which water quality affects the amount of light which is available at different depths within the water column. And this is pertinent because light is a limiting factor for primary production. And the photic zone is the region of the water column where there's sufficient light to support primary production. But the depth of the photic zone varies widely across different ocean areas. It can be very deep as 200 meters in the open ocean, far from land and where nutrient levels are generally low. And the photic zone can be relatively narrow, or relatively shallow in areas where there is intensive turbidity or other factors that reduce the amount of light able to penetrate the water. And we described earlier that the light in different wavelengths ascends to different depths. And here you can see a picture taken at about 15 meters, I think, maybe a little deeper on the Flower Garden banks. And you'll notice that there are a variety of fish that are deep red, these big eyes, and vermilion snappers. And they're red because the photographer, in this case me, provided artificial light using a strobe. But if you took the light away, these red fish would appear brown or dark colored because they're, at this depth there is no available red light. Okay, so to understand the way in which light is able to penetrate, we have to understand what's called the extinction factor or the attenuation factor for light as it moves through the water column. And we said that this is determined by a simple, that the determination is for all wavelengths of light is expressed in this exponential decay equation, where I is the intensity at some depth z, and that's related to the depth at the surface, depth 0, raised to the factor of e raised to the factor of minus k. That's the attenuation factor that makes light less at every level of z, the depth. So to understand how this works and calculate that, let's take an example. And the example I gave is from the Flower Garden banks, where we deployed a light sensor on the bottom at approximately 15 meters depth. And this light sensor, this light bulb-like sensor is recording the light levels in the water. So the light that penetrates down through the water column 15 meters to the bottom. And this is the kind of light that would support primary production either by free-swimming phytoplankton or by dinoflagellate zooxanthellae symbionts resident in the corals that live at the Flower Garden banks. Okay, so how should we understand this? And so for the monitoring experiment, I was part of a study that was studying the conditions at the Flower Garden banks. And my job was to try to understand physiological factors, oceanographic factors that determine primary production. And so I was concerned to measure light levels. And so to do that, I placed an instrument, the same kind of light measuring intensity instrument on an oil platform. And the oil platform is at 0 meters, so I0, and I measured the incoming light. So this is light in the photosynthetically active radiation, the PAR range, from approximately 350 to approximately 700 nanometers. So that's the PAR light. And so this PAR sensor measured the irradiance at that. So let's look at an example here, and we'll take the example of February 1999, when the I0 was equal to approximately 2. And these are measures of irradiance expressed in moles per square meter per hour, moles of light. So light can be measured in moles. This unit is also sometimes referred to as Einsteins. Okay, so in February of 1999, 1999, we were measuring approximately 2 moles at the surface. Okay, and at depth in February 1999, we were getting about 0.2 moles. Okay, so you know, to make our calculation, to calculate what the attenuation factor, the K factor would be, we would apply that formula. So the formula in this case was, I hope this works, I sorry, I'm having trouble with my pen tablet. Give me a second here. All right. So our expression is I at some depth is equal to I at 0 depth times E to the negative K times Z. All right, so if we want to calculate what this is, we're saying here that 0.2, which is what we measured at the bottom, is equal to 2 times E to the negative KZ. And if we want to get this, we divide both sides by 2, so we get 0.1 is equal to E to the negative K times Z. All right? And if we want to then remove this, we take the negative log. So we say the natural log. So we say that the Ln equals negative K times depth Z. All right. So how would I calculate that? A calculator. And I'm saying that 0.1, take the negative log of that, is equal to minus K times Z. Since Z is 15, we'll divide by 15, and that equals 0.15. All right. So negative 0.15. So for this example, with a measurement of 0.2 at 15 meters depth, based on a incoming radiation at 0 meters depth of 2, we get a negative K of approximately negative 0.15. Right? And so if we close all that, look at the actual attenuation that we recorded in February of 5, we can see that in February we're approximately at 0.15. And this, of course, goes up and down at different times. The dark line is the 7-day moving average. Okay, so that was how you would calculate the negative K based on measured light levels in the water column. Any questions about that?
Could you go back to your work real quick? I didn't get to write it all down.
I'm sorry, could you repeat yourself? I didn't quite hear you.
Oh, can you go back to the written work real quick?
The written work?
Just wrote out.
You mean this?
Mm-hmm. Sorry, I just wanted to get the last part.
Okay.
Okay, I'm good. Thank you.
Everybody got that? So it's a pretty simple, and you know, interestingly, this is a useful equation because it doesn't have to be negative. So if I plugged in interest rates, for example, and I said, let me clear all this. I don't want to clear all this. Well, if I plugged in, you know, your money, money at some time t is equal to the money invested times 0 times e to the interest rate times time, you could make the same calculation for how much your money would grow based on a rate of increase raised to an exponent. So, for example, if you were you had an investment that was paying you 15% per year, and you made an initial investment of say your initial investment, so S0 is equal to, let's say, $1,000. And then your T is equal to 5 years, let's say, and your interest rate is equal to 0.15. You could plug in those same numbers, use that same equation, and calculate what your yield would be for compounding the interest over that time. I'm not going to do those calculations, but that's just a way of understanding how these simple exponential equations can produce answers that are useful in the real world. Okay, so I'm going to quit out of here, and we'll go back to this to the lecture. So that was a question we had, and that was you know, it's important, of course, for understanding the compensation depth. And so this compensation depth, where, you know, the respiration is equal to photosynthesis, this could be a variable number depending on the conditions, winter versus summer, you know, coastal water versus offshore water. So this is a variable number, this compensation depth. But if you knew what the compensation depth, if you knew what the minimum amount of light level needed for respiration and production, you could calculate what that would be, and that's how you would make that calculation. It's the bottom of the euphotic zone. All right, let me switch over to the second topic that we're taking up this week, which is nutrients from the sea. So let me escape from here. And we'll go to so you remember that we're talking about the ways in which this primary production and the production of fish populations, the supporting of fish populations due to the marine ecosystem processes, is exploited by human beings. And we said that this is a very long-term process, that human beings have been extracting nutrients from the sea in the form of fish and kelp and other products for all of recorded history and even before. So, you know, 12,000, 13,000-year-old footprints indicating, you know, coastal populations of human beings who were undoubtedly exploiting that. And we also said we have similar archaeological evidence and anthropological reliance on marine production is visible in our own area in the form of shell middens. So human beings are well adapted to extracting nutrients from the sea. And so we're trying to understand what the limits on that are, and the way in which modern techniques have contributed to that. Okay. And I talked about you know, technological achievements, and I'm referring here specifically to the development of this hydraulically driven block, the Curetic power block, which is used to haul nets. Previous to the invention of this, all nets were hauled by hand. So you'd have a large group, 15 to 20 people, who would have to, you know, strain and stress to, you know, to hoist these nets on board. And we showed examples of the traditional sea shanties sung by the net haulers in Chesapeake Bay and South Carolina, who you know, used to haul those nets by hand back in the old days. I guess in the 50s, because nowadays it's all done by power blocks. And we introduced the concept of anchovies, and we're going to talk about anchovies as an example of a pelagic fish that became an important basis of a fishery. But in the specific context of the lecture here, we talked first about the way in which bird guano produced by populations of birds which feed on these anchovy produced so much guano, and the guano was a very effective fertilizer, that there was for a time in the 18th century a practice of extracting this material and using it for fertilizer. In fact, you can still purchase bird guano. I'm not sure if it comes from the Guano Islands because these have mostly been depleted, but you can in fact purchase bird guano as a form of fertilizer. I've seen it online. I think you can buy it through Amazon. So this is still a practice which obtains. Okay. The question then is, why? What do cormorants eat? And cormorants eat this pelagic fish, which we call anchovy, and anchovy are small fish. They're just a couple of inches long, and they live in the upper. We refer to them as pelagic fish because they live up in the top in the photic zone. They reproduce and after reproduction, after birth, they reach reproductive age within about a year. They live less than 2 years. And so the population is, with that kind of a sort of K-factored reproductive strategy, the population can respond quickly to major changes in environmental conditions. And we'll see that there are such changes that occur. Now these anchovy, the populations of anchovy, are supported by high levels of productivity in the photic zone offshore South America. And those high levels of productivity are both at the level of anchovy, which are primary consumers of secondary consumers, I suppose. So the anchovy eat the zooplankton, which eat the phytoplankton, which are supported by upwelling. And the upwelling is generated by coastal winds, and the coastal winds deflect water offshore. And the water that's deflected offshore is replaced by upwelling water from depth. That upwelling water is rich in nutrients, and those nutrients support abundant primary production, primary consumption, and secondary consumers such as anchovy. Okay? And this is the normal weather condition. There's also a condition called El Nino, and we're familiar with El Nino because it impacts our weather. It impacts the occurrence of hurricanes. Last year was not, last hurricane season was not an El Nino year, and as a consequence, we had quite a few hurricanes. So El Nino years tend to, there's higher upper level winds in the atmosphere. Those upper level winds tend to impede hurricane formation. They also shift the low pressure center, which typically is located in the Western Pacific. They shift that towards the Central or Eastern Pacific. And with the shifting of that low pressure center, the winds which drive the upwelling along the South American coast, those winds die down, and you have different conditions. And with the failure of the winds, the upwelling tends to stop. And so because, as we talked about, phytoplankton, they're not like the trees, they're living, a day or so. So they're very responsive to conditions and fluctuations in those conditions. So if upwelling stops, very quickly, the availability of nutrients starts to limit the primary production and the zooplankton that feed off the primary production and the anchovy which feed off the zooplankton. So this tightly coupled food web breaks down when the supply of nutrients fails. So this is a sort of a classic example of how ocean conditions, ocean ecosystems are dependent on environmental factors. And in this case, the environmental factors are dynamic. They're changing, sort of on decadal scales with the occurrence of El Nino years. So under El Nino conditions, the anchovy move closer to the coast. The birds, the cormorants that feed on them, die back. But that's a temporary condition. And as soon as the El Nino conditions dissipate and the normal wind regime resumes, then that upwelling starts again and the whole system can respond. Okay? So the anchovy can move further offshore. The bird populations can recover and grow back. And the system can return to quote unquote normal conditions of high productivity. Well, these El Nino years don't occur all the time. So these are pictures that I took in 2015, and we're offshore Chile in this case, and not Peru, but they're very similar ecosystems. And this is a colony of these Guanay cormorants. You can see how densely packed they tend to be, but this is actually a very small colony on an island which is a marine reserve. So people are not allowed to go on board this island, and the expedition that I was with were fortunate to get a little tour, and so we drove around and got to see the birds and these little guys here are penguins. There's a species of penguin, rock hopping penguin, and they go up and down, and there are other species of birds. It's a very interesting environment to look at. Here's a closer view, not the same one that I was showing you, but another place where there's a colony. And in this case, you can see that the numbers of birds are greatly reduced. And you can also see that conditions have changed. And so unusually for 2015, when I was there, I think we did have an El Nino on, and there were a lot of rain falling. And so some of these desert islands hadn't received rain in years. When the rains fall, it sort of washes away the guano layer. You can see these sort of rivulets formed by rainwater washing the guano away. And so these are bad conditions for the cormorants, and this small size of this colony reflects the general failure of conditions for the birds. Okay. Well, let's turn back the clock to the late 1960s, early 1970s, and the invention, the introduction of the Pyretic power block to the Peruvian anchovy fishery really revolutionized that fishery. So here we see, this is not a picture that I took, but this is a purse seining ship, and I'll explain what purse seines are in a minute. We already have, I guess. And you can see here there's a Pyretic power block, which is pulling on this net rope here, and they're landing a big catch of anchovies. And just remember that some of the terms that we need. So this is a operation which is targeting pelagic fish. Pelagic fish are those fish that primarily live in the photic zone. There are other types of fish, and as we talk about fishing and fisheries in the course of this lecture, other terms that you need to know are demersal, and demersal fish are those that live on or near the bottom, and they're also midwater fish, and they live within the water column. So an example of midwater fish, which we've talked about, or you mentioned, I guess, in the video, were myctophid lanternfish, and they're small fish that live within the water column. They're one of the most abundant fish on the planet, but to date there's really not a fishery for myctophids, although with the failure of some other fish stocks, there's begun to be some exploration or some consideration for trying to catch midwater fish. But primarily fisheries focus on either pelagic fish or demersal fish. Okay. So in the case of the anchovy, this operation is targeting the pelagic populations on anchovy offshore South America and the Pacific Ocean. And you can see, as this net comes on board, you get a sense of, the incredible amount of biomass that this population reflects or includes. And so this is a haul of fish. This is probably, many tons of these little teeny tiny fish. They'll be brought on board like this, and then they'll either dipper them out with a sort of a net-like device, or modern ships, probably this one here, would actually use a pump. So they lower a big pump down in, and then just pump out the anchovy into holding pens. So the anchovy are edible, and I've had them. They're very nice, fried in oil with, they sort of crisp up, and they're crunchy and good. But generally, anchovy are not eaten. I guess you can get them on pizza sometimes, but generally speaking, they're not a big food fish. But what they are used for are the production of fish meal. So here's a picture of the anchovy. So this is what we'd see in the hold of that ship after the anchovy had been pumped out of the net when it came on board. And so in the early 60s, with the early 1960s, with the introduction of the Puretic power block, the traditional anchovy fishery, really became tremendously more productive, because instead of having to haul these nets by hand, they can use mechanized means to haul them up. And so the fleet catching anchovy expanded very rapidly. And instead of using the anchovy directly as a foodstuff, it was ground up and processed to make fish meal. And fish meal is a protein and nutrient-rich powder-like substance. It's used as part of animal feed. Some parts of it are used in production of things like margarine. So you can buy margarine that's based off fish meal or fish oil. And it became a very, very valuable commodity in the late 1960s and early 70s. And all of the experts from the United Nations Food and Agricultural Program, FAO, they all looked at the models and they said, wow, you can expand this anchovy fishery without worrying, because you're not taking as many anchovy as you could. You could harvest even more. And so they predicted that the fleet could grow more, and there was a lot of investment. Capitalists, invested money and bought more fish meal ships, and fish meal became a very important export commodity from Peru and Chile. And there was a huge economic boom. Well, that all came to the end in 1973, when for the first time, when there was a heavily developed anchovy fleet fishery, the El Nino conditions returned. And with the return of El Nino conditions, as we discussed previously, the upwelling of nutrients stopped. When the upwelling of nutrients stopped, the production of primary production by the phytoplankton and zooplankton that feed on those, and the anchovy that fed on the zooplankton, that crashed. And so what you get here is, so here's a growth, and you can see, in the 60s, when the Puretic block is introduced, there's this huge explosion in catches of anchoveta, and these are catches measured in millions of tons. So we were looking at about 12 million tons being caught in 1970, and then in 1973, along comes this sort of overnight, this El Nino year, the failure of upwelling, and the crash of the population. Well, this El Nino is, not a anthropogenic consequence. This is a natural cycle. What actually causes the timing of El Nino versus La Nina years is still a matter of active research. One of our professors here at Florida State University, Dr. Clark, is a world expert on the El Nino, and so he's tried to model that. There's still a lot of information. We're getting to understand it better. But back in the 70s, nobody had any idea, what caused El Nino to occur or not occur. But it was a natural phenomenon. Now, under natural conditions, when El Nino passed, the anchovy would move offshore, the birds would recover, and the ecosystem would return to quote unquote normal levels. However, in the case of the Peruvian anchovy fishery, instead of the dependence of the ecosystem on large production of anchovy, that all collapsed. But the fishing boats still had to pay their mortgages, essentially. So there was this huge, heavily capitalized industry depending on landing anchovy. And so instead of suspending operations, the fishing boats essentially chased the anchovy that moved near shore and continued catching them. So what would this do? This had the consequence of driving down the population and slowing the recovery of the ecosystem when non-El Nino conditions returned. And likewise, the bird populations, instead of being able to rebound quickly when the populations of anchovy returned, they were also reduced. And so maybe it's a good thing that we don't depend on guano for fertilizer anymore. And so this cycle here, so this lasted, the decline of the anchovy fishery lasted, over 10 years. So it was a long time before it recovered. And then when it recovered, they kind of went right back into this cycle of overproduction. And then there was another El Nino year. So this was all kind of predictable. And this cycle of high landings followed by crash, followed by high landings, is called a boom and bust cycle. Sometimes you go through multiple cycles, and sometimes you just have a boom and then a bust, and there isn't a recovery. One of the reasons that you can have this boom and bust cycle with pelagic fish is that those populations respond quickly. They live a short period of time. So fish that live have longer lifespans and take longer to reach maturity would take longer to recover if their populations were reduced to a particularly low size. Okay? So this is an example of the sort of interdependence of different factors, physical oceanographic factors, ecosystem responses, and then in this case, the way in which a heavily capitalized industrial fishery sort of altered the balance of processes in the ecosystem. Okay, so that's an example, sort of a cautionary tale of what can go wrong in fisheries. And I wish I had better news, but the fact is that most of the world's fisheries are overexploited, and it's very difficult for human enterprise to properly manage these sorts of natural ecosystems, and particularly when they depend on very carefully calibrated takings and landings. So let's talk a little bit more and think a little bit more about global fisheries. So here is a description of the global fishing and ecosystems, and this is sort of showing us high plankton production areas. And where do we get high plankton production? Well, upwelling that we talked about. This is coastal upwelling. Here is equatorial upwelling. There's relatively good upwelling in the Gulf of Mexico due to action of the loop current and other processes. There's high plankton production offshore Africa. And so areas where there's coastal upwelling get these high levels. There's also upwelling and high plankton production in the Arctic and Antarctic regions. And so these are areas of high productivity. So these are where the plankton are, and generally speaking, that's going to determine where the fish are. And we'll see that, when we look at this, there's actually a very tight relationship between, where primary production is high and where fish populations are high, and then where fishing operations go to exploit those. Okay, so that's one thing that we're seeing on this map. The other thing that we see on this map is this sort of brownish red line. And this is a very important line for marine policy, marine management, and the control of marine resources worldwide. Because what this line is showing is the exclusive economic zone, which extends out by treaty 200 miles offshore the countries, relative countries. And so here in South America, the EEZ, and this is Brazil, so the Brazilian EEZ extends out about 200 nautical miles from the coast. And here there are some little islands, and so the EEZ is extended further. Likewise here, further. And down here, this is the Malvinas Islands, also called the Falkland Islands, and so the EEZ is extended further to accommodate that. So the treaty, and this was the Law of the Sea Treaty, was signed back in the 70s, or it was negotiated back in the 70s. Most of the countries in the world signed on to the Law of the Sea Treaty, which established the exclusive economic zone. The United States did not. Congress and the Senate in particular failed to ratify the Law of the Sea. And so as a consequence, the United States is not a party to the law of the sea. However, the United States does tend to honor the exclusive economic zone. And so this exclusive economic zone, gives countries control of mineral resources. And in fact, concern about loss of control of mineral resources was one of the arguments that was used against the United States joining the law of the sea. But it also gives the countries control over fishing offshore. So fishing is in national waters has to honor the and compensate by law the countries, the coastal countries within that EEZ. Okay. So you can see, for example, here on the coast of West Africa, that all these little West African countries, Ghana, Senegal, Gambia, they all have EEZ rights to fishing in their immediate offshore. And as we'll see when we get a little further along, a lot of times those rights, particularly in developing countries, are not honored and are heavily infringed upon with serious consequences. Okay, so there's a brief look at where we might expect to find open ocean fishing resources. They're going to track areas of high productivity, and then where different kinds of conventions control where fishing is. And so another thing to notice in all this is, yeah, okay, there's an EEZ, and that EEZ encompasses a lot of the productive fishing waters, but then there are very large areas where they're totally open ocean. And essentially, those fish don't really belong to any country or nationality, or in fact to any company. So fishery and fish production is kind of a unique concept in the world, particularly open ocean fishing, because the basic commodity that is being exploited, the populations of fish, aren't owned by anyone, and they aren't managed by any particular group. Even within the EEZ, you can say, well, these fish, they're fish in American waters, or fish in Mexican waters, whatever. But there's no company that owns, the actual fish populations. Instead, they're using, particularly increasingly today, heavily capitalized industrial processes to extract these fish. Now, the global production of fish is approximately 100 million tons per year. That's actually been decreasing lately. So that's 100 million tons are produced by fish that are what we can call wild caught fish. There's also about 28 million tons, and that's actually increased, produced by aquaculture. Aquaculture are different from fisheries because in an aquaculture organization or operation, the fish populations that are being produced are owned by whoever has put them in cages and is feeding them up. These are two very different models for producing fish. And 90% of the continental shelves are dominated by a few major fishing nations. And there have been recent failures in years. But I mean, fundamentally, what we're looking at are areas where two factors, the supply of nutrients from upwelling and the availability of sunlight, is going to determine the existence of a productive fishery. So we have very productive fisheries in the high Arctic areas, but they're productive only during the times of summertime, North American, Northern Hemisphere summer or Southern Hemisphere summer. And then in the more temperate regions, you have abundant sunlight year round. Okay, and in recent years, many of the populations that have traditionally been exploited by fishing operations have failed. So by failed, I mean that the population has dwindled to the point where fishing operations not only cannot easily realize a profit, but that the drive to continue fishing and keep operations going sometimes pushes the population beyond the point where it can rapidly recover. And that's what we would call a failed fishery or a crashed fishery. And unfortunately, there are many examples of those, and we're going to explore that a little bit. Okay. Now, to understand, how fish populations respond to changing conditions, and how, in particular, fish populations might support a fishery in a sustainable sense, and sort of for multiple years, we need to look at some fundamental processes that control population growth. We're going to, in particular, we're going to look what's called the logistic curve. And you've seen this before. I showed you this when we were talking about life in the ocean initially. And so in particular, we're going to look at the logistic curve, which is based on the idea that small populations with abundant resources will grow, will increase at exponential rate, and that eventually over time, the increase of a population will exhaust or fully utilize the resources that are available to it, and the rate of population growth slows and then stabilizes around some carrying capacity. They reach their logistic carrying capacity at some higher level, and at that point the rate of population growth becomes essentially zero. So what does a logistic curve look like? So here's a hypothetical logistic curve, and this is being specifically applied to understanding fisheries. So the logistic curve says that if we start with a zero population, and then that population is going to grow and expand, initially there'll be a J-shaped expansion, so a pure exponential expansion, and then as the population increases in size, the limits begin more and more to affect the rate of growth, and so the rate of growth is slowing, and you get this S-shaped curve. So you start out with a J-shaped curve initially, very rapid rate of growth because there's a population that's exploiting abundant resources. There's not a lot of competition, and then that J-shaped curve becomes a sort of an S-shaped curve, and then stabilizes around some point there. I'm actually going to change the order of slides here a little bit. Go back here. So, this is perhaps a better way to look at this. So there's an initial J curve, and that gives rise to an S curve as environmental resistance increasingly slows the rate of growth. And at some point or another, the population stabilizes around the carrying capacity. So what do we mean by carrying capacity? We mean the availability within a given ecosystem, and that's a fuzzy boundary, but we agree on that. The availability of necessary ecological components, has reached its maximum, sort of saturated. And, a population will typically oscillate around that carrying capacity due to varying conditions, weather, temperature, production of other stuff, as we've seen with the example of Peruvian anchovy. So in the case of Peruvian anchovy, the population, initially grew very rapidly, and then it stabilized around a carrying capacity. But that, stabilized included, population crashes episodically when El Nino conditions came along. So this carrying capacity, is a lot of times very hard to calculate, and the rate there, what the actual value of the carrying capacity is can also be difficult to understand. All right, and so then here's this logistic curve. Now, in the 1950s, particularly in Britain, the British fishing industry, so the British have always been seafaring and fishing nation. Also France was also important there, but in particular Britain had population fishing fleets that would go operate in the North Sea and off Iceland and a lot of different places, and all that fishing operation stopped during World War II. And then after World War II, there were food shortages in the UK, and there was a lot of attention around how can we return to fishing and then maximize the amount of fish that we're able to produce. And so in the 50s, there were a lot of scientific work to try to come up with theories that would explain or would guide fisheries management to the point where a sustainable yield could be obtained. And so the idea is, if we look back at this logistic curve, that the most rapid rate of growth, for this S-shaped logistic curve occurs in theory when the population size is about 1/2 of the carrying capacity. So what does that mean? So the theory of maximum sustainable yield suggests that if you have a population that's reduced in size from its carrying capacity to approximately 1/2 of the carrying capacity, then each year there'll be some quote unquote excess production. The excess production is the growth of the population that's trying to return the population, or would have the result of returning the population to its carrying capacity. And that excess population could be extracted essentially on a long-term basis. So this is saying that the MSY level is equal to 1/2 of the population size. And so the surplus recruitment over time, this is the potential harvest, is going to come if we reduce the fish population to 1/2 of its carrying capacity size. Okay. So this was the theory, and this was put out there, and a lot of management and a lot of decisions were made, with the optimistic thought that that we would be able to calculate what these carrying capacities were, and that fishing, scientific fisheries management would be able to limit fishing and control harvests to the point where yields from fishing operations and particular fish populations could be sustained over multiple years. Well, what do we need, and what are the assumptions that lie behind the maximum sustainable yield theoretical model? Well, one idea is that the population must have one exact carrying capacity, which is predictable from the logistic curve. Okay, well, we can already see that one exact carrying capacity assumption is quite fallible. Because in the example of the anchovy, the carrying capacity in a non-El Nino year is up here, and then when the El Nino conditions come along, and El Nino conditions can last for several years, the carrying capacity is actually reduced very significantly. So if your fisheries management model says that we need to reduce the population to 1/2 of the carrying capacity, and then we can extract the excess from that, in perpetuity, well, that carrying capacity is wrong. That reduction in population size and the level of fishing effort to reduce the population of that size is wrong if El Nino conditions lower the carrying capacities for some period of time. So, population has to have one exact carrying capacity, and we know that with variable environmental conditions, this is not going to occur. And moreover, this assumes that managers will be able to know what the carrying capacity is and to know what the true size of the population is. And more than that, there has to be near perfect cooperation among all the factors that are acting to harvest the population. And this includes not just the fishing operations that are trying to extract the fish from the population, but also natural factors. So one of the things that the modelers really got wrong back in the 70s when they were trying to figure out why, oh my goodness, all the population has crashed, the fisheries have crashed, all these expensive fishing ships are not returning with enough catch to pay their bills, what's gone wrong? And they quickly, sort of calculated, oh, it's the El Nino, and and maybe it'll come back after the El Nino recovers. And so they built in, sort of a recovery factor. And unfortunately, they left out of the recovery factor the natural predators, the cormorants that we talked about so much in the beginning of this lecture. So they left those out, and they said, oh, well, okay, once the El Nino is gone, you can return to harvesting at such and such a level. But guess what? That wasn't the only process that was exploiting the population. There were also the birds eating the anchovy, and not just the birds, but then also tuna and other larger predators who also fed on that. So leaving out the full ecological food web that a population supports can lead to some very, very wrong assumptions. So what this is saying is that the maximum sustainable population size, if the population is estimated correctly, and if there is one true carrying capacity, then you should be able to get this yield over time. So the population is estimated correctly, and you can do this. But if the population is overestimated because the carrying capacity is not fully understood, or because the managers fail to reckon with seabirds and other predators who are also going to exploit a recovered population, that population is overestimated. And in those conditions, fishing continues, exploitation continues, and it continues to drive down the fish towards a much lower level. Now, one of the truisms is that there'll never be fishing operations will never catch the last fish, because the fishing boats won't be able to pay their fuel bills and their personnel costs and whatever when the population size is that small. In practice, that doesn't work, and there are many fisheries where the fleet is so large and the economic pressures on the fishing operations are so great that they will literally chase the last fish. And this, unfortunately, has happened to quite a number of global fishing operations. This is what's happening with the bluefin tuna. It's already happened with Atlantic cod. It's happened, on and off with the brown shrimp population of the Gulf of Mexico. So there are many cases in which this MSY and rational fisheries management has failed to produce over time a sustainable yield. I don't want to be, I don't want to totally disparage fishing management and fishing limits, because the National Marine Fisheries Service and MFS has successfully managed some fisheries, and they do propose quotas, and they do limit the operation of the fleets in such a way that yields continue. But generally, this is a very challenging operation, and by and large, fisheries management has failed to produce sustainable yields for most of the populations that have been managed. Okay, so under those conditions, we can look at, can sort of start to consider a lot of different factors. So here's this multiple sustainable yield, maximum sustainable yield sort of idea. So this is an exploitation rate somewhere in the half of the population. This is sort of measuring this is the exploitation rate, so this is the rate of removal. And so around here, around the 1/2 level is where you should be getting the maximum sustainable yield. And then, when the population drives, it should be rebuilding. And if you go push it further, so if you're exploiting at a greater rate than the maximum sustainable yield, what you're doing is something called overfishing. You're overfishing this theoretical maximum sustainable yield. When does that occur? And so what happens? Other things start to respond. And so this shows how other factors, other measurements of the population are going to change, under different conditions of exploitation, different yield scenarios. And so when if there's rebuilding of the fisheries, the fishery is temporarily closed or limited, the total biomass is going to return to this 100% of carrying capacity. And not only that, but the other measures of the population size and population health are also going to adjust. And so here's a factor called Lmax. And what Lmax is measuring is the maximum length of fish in the catch. And so if we think about that, a fishing population, fishermen generally target the bigger fish. As anyone who's been fishing knows, you'd rather catch a big fish than a little fish, generally speaking. And so, when fishing operations sort of exceed the size, the Lmax, the average maximum length of the catch starts to go down. And, it can decrease quite a bit. And so, there's a couple of problems with this. One problem is that for most fish species, a large proportion of the reproduction is completed by the older female fish. So big, anybody who's been fishing, I don't know how many of you are red snapper fishers, for example. Well, we talk about the hog snappers, the big, large female red snapper. Well, those are the ones that produce vastly more eggs and vastly more reproduction than the smaller, younger individuals. And so if you remove these large individuals, particularly the larger females, then the reproductive rate for the population can be heavily impacted. So, this is over time. And what this is measuring, unfortunately, are collapsed species. And these are species where the population has dropped below the point where, any kind of a yield can be obtained. What is the advantage? What is the the motivation for trying to keep fishing in this region? Well, it's maintaining biodiversity, maintaining the health of marine ecosystems, maintaining the high catch, maintaining high employment. These are all measures of what happens. And this example here by Worm et al., 2009, this is a sort of a key paper on fisheries management, and the unfortunate story of the heavy overexploitation of most fisheries. Okay, so what I'm saying here, and what Worm and his colleagues also predicted, I guess it's VERM, was that there are many species that are being overfished. Well, what are some indicators of overfishing? Decline in the catch. So fewer fish are being landed. Okay, so here's an important concept here. If you're talking about catch and you're trying to understand how landings have changed over time, you have to adjust the catch to make allowance for what sort of effort is happening. So the easy example is that a large fishing vessel with lots of avionics and navigation, sonar, fish finders for finding the fish, heavily mechanized net handling. Generally speaking, you would expect a fishing operation, a fishing vessel of that size to catch more fish than a much smaller fishing vessel. And the disparity between heavily mechanized, heavily capitalized fishing operations and more modest fishing operations is particularly acute, as we'll see when we compare industrial fishing to artisanal fishing in developing countries. So in order to fully use catch as a metric of the health of the fish population, we have to adjust the catch for effort. And the term is catch per unit of effort. And so, or CPUE. And so reductions in the catch per unit of effort are indication of a declining fishery, overfishing. reduction in the average size of the catch. The average size of individuals that are caught is also a measure or indication of overfishing. A sharp decline in the seasonal fishing, so that, you know, if there's a particular season, herring season or something like that, you know, this has sort of been an annual event, and then the fishing fleet goes out during that particular season, and all of a sudden there are no fish there, you know, that's an indication that overfishing has occurred in the practice. So, however, in practice, overfishing is difficult to detect before it happens. So, you know, catches are high, the average size of the catch is good, everything is fine, and then suddenly it crashes. That's, you know, very often the way in which things happen. Well, there's another problem when we try to understand fishing, is that what are we comparing it to? If we're talking about decline in catch or, you know, reduction in average size of the fish, you know, we have to understand what baseline we're making that comparison to. And this is challenging in the case of fish. And there's something called shifting baselines, or declining decreasing baselines that obtain when we measure fisheries. And here I'm going to show you some examples of this, you know, which were collected. This is a valid set of observations, scientific observations. And so here we are. This is a picture from, this is taken from Key West. And in Key West, this ship, the Greyhound 2, goes out from Key West every day, and it takes people with them, and offshore they go, and they come back at the end of the day, and this is their catch. Wow, what did they catch? Well, mostly what they're catching are Goliath groupers. Now these big fish, there's also snowy groupers and other species of groupers, but these groupers are a particular form of demersal fish. They live on the bottom, and they're typically caught with some form of hook and line. So the Greyhound 2 has gone out, and they've come back at the end of the day with this amazing, you know, catch of groupers. Wow, good for them. Must have been a fun day. All right, well, let's fast forward to the 1980s. Well, here we are. We're still in in Key West, and the fishermen have gone out, and they've had a fun day, they've all gotten a little sunburned, and they've come back, and these are all the fish that they've caught. Well, what do you see when you look at this this picture here? You know, this is sort of more anecdotal, but it's still can be quantified, because look, there's been a total change in the species of fish that are present. Whereas the previous year they were all catching these grouper, you know, now there's only one grouper in this whole. Maybe there's another one over here, but generally speaking, they've shifted, and now they're coming back with snappers and caravel and a variety of other fish species that they might have caught those before, but they threw them back because they were targeting a particular species. But nonetheless, they've caught a big pile of fish there. Everybody who went out in the boat is going to go home with a freezer full of fish, and you know, everybody's looking pretty happy. Okay, well, let's go to another picture. Here we are, and we're still back with the Greyhound. This isn't the Greyhound 2, it's the Greyhound 5. This is in 2007, and wow, what do we see here? Well, first of all, not nearly as many fish. The fish are much smaller. There is one grouper here, but you know, the snapper, the red snapper, have given way to vermilion snapper and yellowtail snapper, and these are fish that you know, a lot of these are more planktivorous fish that are eating zooplankton, fish that are you know, lower on the food chain, that they're not the top predators. And then you also have fish like this dogfish that would have been considered a junk fish previously. Nobody would have even brought it home. They would have just cut it loose. But now this fish is being landed. And so what can we say here? Now, you know, these people are still paying their money, and they're still going offshore. They're still catching all these fish. They're probably still having fun out there. And, you know, as a measure of success, they might come home happy and might be return customers. But we can see, you know, by making this comparison over, you know, something like 40 years, that the baseline has shifted, has decreased. So there's been a declining baseline for measurement. Right? And so, that's another challenge because generally speaking, the ecosystem, the marine ecosystems that we exploit and the species of marine organisms that, are available in the ocean have shifted dramatically due to human interaction over the past century or so. All right, now how can we measure this? How can we measure this trend? Well, here's an interesting way of looking at this. So what this is a global picture, and this is from FAO, and this isn't updated. This stops at 2004. This is from the Food and Agriculture Organization, the United Nations. And so what they're keeping track of are the number of decked fishing vessels. And what's a decked fishing vessel? Well, a decked fishing vessel will generally, have a diesel motor. Will have ability to store the fish below decks, probably an ability to stay out overnight. And so these are the larger types of fishing vessels. And so we go from, there's a pretty rapid increase all the way from the 70s through the 90s. So there's an increase here. More, you could argue that there is a little bit of exponential increase all the way into the 90s, and then it sort of stabilizes and stops increasing. So I'm showing you this, and I hope that you kind of think back to the logistic curve that we showed earlier. So let's see. Remember how this is a trend which is indicating the global overcapacity of the fishing effort. And this decline, or this stabilization in the rate of growth in this case not of a particular fish species, but of decked fishing vessels, that's increasing over time. Okay, and we can measure this, and that's like the logistic curve. So the human exploitation of fish is following this same pattern of rapid increase and then stabilizing around some high capacity. Well, if you go up and down the Gulf Coast here, particularly Louisiana, Texas, Alabama, go to a dock, you'll see dozens and dozens of these shrimp boats. And they're tied up at the dock, and there's only a few weeks of the year that there's enough fish out there for them to go out and fish, and so this is sort of idle capacity. Many more fish than are needed, and it's an indication of overexploitation. In this case, these are ocean-going shrimp boats, so they would be targeting the brown shrimp, Campechium Penaeus astecus. Okay, so there's an example now. I want to talk some more about international examples. I talked about the difference in catch per unit of effort. So in Africa, particularly on the west coast of Africa, if you recall when I showed you the picture of where fishing zones are, the west coast of Africa was a particularly productive region. And the native folks in Africa go out in these open boats. They go way offshore. And the boats are pretty seaworthy. They're able to tolerate heavy conditions, and but they're in direct competition with industrial boats. And so artisanal fishing competes with factory trawling. And that competition is not one that's going to go favorably for the fish. And I'm going to put up an example of that. I'll show you a video that you'll post that sort of goes into more detail here. When we're concerned, a lot of times you get bad press about the pirates, the sort of African pirates that are attacking ships. Well, a lot of times the pirates are these fishing folk whose way of life has been upended and whose basic resource has been stolen by these industrial fishing operations that come in and operate without permission. And so generally, this is sort of showing how well, I want to draw your attention to particularly to this graph. What this is showing is how the fishing nations, Russia, France, Spain, Japan, Korea, that they're all targeting, Africa for, fishing with these heavily industrialized massive trawlers. And so the local people are in direct competition. And a lot of times the industrial operations ignore or defeat the exclusive economic zone. And so there's a, pirate is in the eyes of the beholder in one sense. And from my personal perspective, I consider the industrial fishing people to be much more piratical in their approach than I do the fishermen who are displaced and forced into other lines of work by that industrial change. Okay, so I'll put up a video that sort of covers a lot of this that you'll be able to see. All right, I want to talk a little bit more about, so up until now we've been talking about pelagic fish, well, I want to talk about a particular fish called the orange roughy. This is a catch of orange roughy, and these fish are being caught with a trawl net. I'll explain what a trawl net is. But the orange roughy, this is a poster child of an unsustainable fishery, because the roughy live on deep seamounts. By deep, I mean 500, 600, 700 meters. And so these populations were way below the depth that would have normally traditionally been exploited by fishing operations. But what happened in the mid-90s and mid-70s was that the countries of Australia and New Zealand made a very careful mapping of seamounts, and they located all the seamounts. And when the fishing operations figured out where these seamounts were, they were able to go out and they constructed these special kinds of trawl nets that had big chains and rollers so that they could go over the corals that were on the bottom. And they began catching these orange roughy. Well, initially, the landings were great. They got huge numbers of fish because the populations hadn't been exploited. And so the initial landings were great. But the thing is that the orange roughy are a very, very slow growing fish. They require 30 to 40 to even 50 years to reach reproductive maturity, and individuals can live well over a century. So under those conditions, that's very different from the anchovy. So if you reduce that population, you reduce an anchovy population, drive it down for a couple of years, when conditions improve, the population can easily rebound. Not the case with orange roughy. So orange roughy, is an example of an unsustainable fish species. Unfortunately, you can still buy orange roughy in public, although lately I haven't seen it. I took this picture a couple of years ago. And I always threaten my students in oceanography that if ever I find out that you're eating orange roughy, well, I don't know what I'd actually do, but don't eat orange roughy. It's not a sustainable fish, despite the fact that Publix puts this little natural caught fishing sign on here. I don't know what that means, but it's not an example of a fish. And in fact, generally speaking, seafood, the availability of seafood has changed pretty markedly. So if we go to like Long John Silver's, which you might think of as a seafood restaurant, and look at what's actually being offered, most of what's being offered are shrimp. Well, shrimp are farm raised for the most part, catfish, and then, sort of other things that are sort of fish-like, and you don't know exactly what they are. And, a typical menu from a seafood restaurant, what's missing here? Well, fish are missing. You got flounder, oysters, clams, scallops, deviled crab, shrimp, but actual fish, well, the choices are whiting, tilapia, trout, or catfish. These are all farmed species. So increasingly, the availability of wild caught fish for human seafood consumption has started to become limited. Other features of eating fish, well, this is something called a fish fillet. I don't know how many of you who have ever had one. You can get this fish. This is a McFish sandwich. I forget what they call it, but you can get them at McDonald's. They're the sort of the fish fillet. Well, it's not really a fillet. It's what's called a fillet. And a fillet is made by caking a fish, and in most cases, the Alaska pollock. Alaska pollock is a midwater fish, so they go out and they catch them with these midwater trawls. And here's a catch of Alaska pollock coming on board in a trawler in the Bering Sea. I didn't take this particular picture, but when I was after I finished my master's degree, I spent 2 months offshore on a Japanese fishing boat catching exactly these kinds of fish. But what McDonald's does is it takes these pollock, which you wouldn't want to eat, particularly if you had one on your plate, because they're kind of soft. They eat plankton, they're midwater fish, and they take them and they grind them up and they process them. And that grinding and processing produces this, nice square patty of fish-like substance called a fish fillet. Well, you can eat it, and it's a source of protein, but it shouldn't be confused with actual seafood. Right, I've got a few minutes left. I want to quickly run through some different fishing methods. So we've talked about trawling. Well, here's an example of trawling. There's a bag-shaped net with long wings, and there's a line of floats across the top of the bag and a line of weights or chain across the bottom of the bag. And then there are two doors, and the doors are angled so that as the net is towed through the water, the doors spread it apart from left to right, while there's the float line holds it open from top to bottom, and the chain weights keep the bottom of the net in contact with the bottom. I mentioned fishing for orange roughy. So on seamounts, you have lots of corals and rocks and things. So what the trawling for orange roughy would do, they put big metal rollers on the bottom lead line. That's the weights on the bottom. And so these rollers would just grind over the corals. And so it was an effective means of catching the fish, but it left behind a swath of destruction for the very fragile component of the ecosystem. And similar things have occurred on Pulley Ridge, where fishing operations have come in, and just a few fishing boats operating over time can destroy corals that take decades or centuries to reproduce. So there's one species. Trawl-caught species include the Atlantic cod, the brown shrimp, Penaeus aztecus, and cod and shrimp have been traditionally some of the most economically important species. But now brown shrimp fishing is limited to a few months of the year, and the Atlantic cod fishery, which was the basis for some of the early colonists coming to North America, that cod fishery has been closed for several years, and there's no indication when it's ever going to be opened again because trawling operations and other operations basically drove it to zero. Another method of fishing, purse seining. This is something we talked about. There's a float line. The float line is dragged around by a skiff. Here's a puretic power block. And so when the purse is completed, the fishing boat pulls in on this purse line and closes the bottom of the net like a purse. And then the net is hauled up and the fish are pumped out of there. So this isn't the main boat. This is the skiff that's helping to deploy the purse seine, try to encircle the fish. And what kind of fish would you catch? You catch menhaden. And we talked about menhaden on Tuesday, anchovety, anchovy. Menhaden are important Gulf of Mexico fish. The Peruvian anchovy was the classic boom and bust fishery. Okay, long lining is another fishing methodology. Using long lines. These lines can be miles long. The problem with them sometimes is they break loose. There's a lot of bycatch. So fish that are caught or organisms that are caught and killed by the fishing line that aren't the target species. And then all these hooks have to be baited. And so there's a big pressure to catch the bait fish. And so long lining is a method of fishing that's particularly. Another fishing method, so long line caught fish would include tuna and swordfish. Although the swordfish fishery and the tuna fisheries, there's still a lot of tuna, but a lot of the fisheries are being closed, and there's very high market value per fish. Okay. Gosh, I've run out of time. Another fishing method I'll refer to is trap fishing. And these are, if anybody's watched The Most Dangerous Catch, this is what they use in the Bering Sea when those guys go out on the crab boats from in Alaska, and they put these traps on the bottom. The crabs enter into the trap and then can't figure their way back out. You can also use traps for catching lobster. Lobster pots are an example of a trawl caught fishery. And I'm going to talk, again, let me just take another minute. I'll keep you and talk about, because this is in the quiz. This is a guy named Daniel Pauly, who looked at methods for estimating fish population sizes and the success of fisheries. And one of the problems in estimating whether or not fishing is happening in a sustainable basis is getting reliable fish catch information, fish statistics. And what Pauly found in a nutshell was that countries tend to lie about their fishing operations. In particular, China has been identified as being a very unreliable reporter. So China, and for various political reasons, managers are always reporting that they're catching more fish than the previous year, because that's what the political system encourages them to do. And so if the fish catches are always being reported as being greater, then how do you know what's really being caught? And Pauly figured out that instead of looking at the actual numbers of fish that were being, or the weight of the fish landings that were coming in, you could look instead at the actual species of fish, because that tended to be more accurate. And just like I showed you with that shifting baselines, if populations are overexploited, you're going to get a shift from fish that are high up in the food chain, higher trophic level fish, to lower trophic level fish. And so Pauly looked at this over time and concluded that the trophic level of global fish and freshwater fish was going down, and as an indication of global overfishing. Okay, well, there's more to cover on the topic of fishing, but I'm going to have to stop there because we've come to the end of our hour. Are there any questions before I leave? Otherwise, you'll see a quiz. Well, I guess one thing I didn't cover that's on the quiz is this question here, and this refers to the shark fishing industry. And so the shark fishery off the east coast of the U.S., shark becomes heavily exploited. And so there's something called a trophic cascade that occurs. So the shark fishing was overfished. And so shark are another example of a fish that's very slow growing. Well, what does shark eat? Shark eats skates and sawfish and deep water dogfish. And so the sharks became, relatively speaking, extinct. And as they became extinct, let's see. So when the sharks were removed, their prey item, which was the cow-nosed rays and other forms of rays, their population increased. And when that population increased, well, what do these guys eat? They eat scallops. And so, as the shark fishery increased, the population of rays, the shark population fisheries increased, the shark populations decreased, population of rays increased, and so they began to more heavily attack the scallops. Well, scallops were a fish species that humans like to catch. And so as an example of a trophic cascade, the exploitation of the shark populations led to a collapse of the scallop fisheries. Okay, so I'll have to stop there, and we'll try to finish off some of this next Tuesday. Next week, the last week of lectures for me, and so after that, it's all going to be student presentations. Okay, any comments or questions? Okay, folks, I think I'll just go ahead and stop the lecture here, and hope you have a good weekend.